Okay, for our topic today, we'll be looking at linear regression method, how to use it. Okay. So linear regression is a very commonly used method and it's actually quite useful for most of the things that we are doing as well. So let's look at it. There are four subtopics here. We'll look at the kind of situation where we can apply linear regression. And before we apply linear regression, we look at the parametric and non-parametric correlation of a given data set. So remember what is parametric, what is non-parametric in the last topic. After that, if there is a relationship, we want to describe the relationship from the data. And then finally, we want to present the data in a graphical form. So this is the four subtopics that we're going to cover today. Now, when do we use linear regression? What are situations we use linear regression? Basically, regression or linear regression is used when we are trying to find whether are there relationship between the variables, between the values. For example, in science, we will look at, is there a relationship between vitamin B in complex intake and energy level? Or in microbiology, is there a relationship between the glucose concentration in the media and the bacterial growth rate? If there is a relationship, how do we describe this relationship in a mathematical form, in an equation? So what we are trying to do is we are trying to find the equation that links up these variables. Okay? That is linear regression. In the previous slide, I talked about this thing known as variables. So there are actually two different types of variables. Okay, you have independent variables and dependent variable. Usually, independent variables, there may be one or more. Dependent variable, usually there's only one. So what are independent variables or variables? They are basically any variables that do not depend on other things in the scope of the equation. Okay. Usually, this is what we sometimes known as the explanatory variables, or in regression terms, they are known as the regressors. Very simply, they are those that you plot on the x-axis. Dependent variables depends on the independent variables. So usually, dependent variables are those that you measure as a result of your independent variables. Okay. So because of that, dependent variables are sometimes known as explained variables, and you plot on the y-axis. So let's look at our example on glucose and bacterial growth rate. What we are trying to find is the relationship between glucose concentration in the media and the bacterial growth rate. So glucose concentration in the media becomes the independent variable. You have different glucose concentration that you want to test. Bacterial growth rate is the one that you measure, and that becomes the dependent variable. In other words, bacterial growth rate depends on the concentration of glucose. Okay, so that is the difference, or there's a link between independent variables and dependent variables. Okay, so how do we compute or calculate the linear correlation coefficient? Now, what is the purpose of correlation? Is essentially, think about this, you have x and y variables. What we are trying to find out for correlation is how well your x and y variables meet each other on the best fit line. That means how close are the data points to the best fit line. So there's actually two common ways that we will do it. One of them is known as the Pearson's product moment correlation coefficient. Commonly, we just call it as Pearson's correlation. Okay. The symbol is R. It can be a small r or it can be a capital R. It doesn't matter. Okay. Now, Pearson's correlation is a parametric measure. Remember, parametric simply means that you assume that the data is normally distributed. In this case, you assume that all the y values are normally distributed and all the x values are normally distributed. The next one that we'll learn is called Spearman rank correlation coefficient. In short, we can call it either Spearman correlation or rank correlation. Okay, the symbol is R subscript S. It can be a small r or capital R, doesn't matter. It is a non-parametric test, which means that it does not assume the data on the x-axis to be normally distributed, neither does it assume the data on the y-axis to be normally distributed. Right. What we need to know is both Pearson's correlation and Spearman correlation actually have a range. It goes from -1 to +1. We look at the absolute value. The closer the absolute value it is to 1, the stronger the relationship between x and y, between the two variables. Okay, it means that if Pearson's correlation or Spearman correlation equals to 0, basically it tells you that there's no relationship. If it is closer to -1, okay, the absolute is still closer to 1, that means there's a negative correlation. X and y is inversely proportional to each other. Okay, if the correlation is more than 0, that means there is a positive relationship. It is directly proportional. So I repeat again, if R value, if the correlation coefficient, be it Spearman or Pearson's, is negative, it simply means that x and y is inversely proportional to each other. If it is positive, more than 0, it is directly proportional to each other. X and y is directly proportional to each other. If it is close to 0 or exactly 0, then there is no relationship. All right. Now let us look at Pearson's correlation coefficient for now. When Pearson's correlation, as I mentioned, if it's positive, it means that as x increases, y increases as well, which means that the gradient will be positive. When it's negative, means that when x increases, y decreases. It's inversely proportional. Okay. When there's no obvious relationship, that means it is neither up or down, it will be close to 0. So you can actually look at the sign, whether it's a positive or negative, to be equivalent to whether it's a positive gradient or negative gradient. This is for Pearson's correlation. Since Pearson's correlation coefficient is for parametric, is a parametric measure, Spearman correlation, sometimes known as rank correlation, is actually a non-parametric measure. Okay, the main word here is your monotonic relationship. Now, monotonic relationship is a function that doesn't really increase or decrease proportionally. So you can have a monotonic increase, monotonic decrease, or it's inversely whatsoever. Okay. If I were to plot the x-axis, or the x values is not going to be what we call as normally distributed. If you plot the y-axis, neither will it be normally distributed. Okay, so that is for Spearman rank correlation. Now, how do we calculate or compute Pearson's correlation coefficient or Spearman correlation coefficient? For Pearson's correlation coefficient, you can simply use the Correll formula in Excel for the x and y values. Okay, you can directly use it for the values, but for Spearman correlation, Excel doesn't have a Spearman correlation function. Correlate or Correll is for Pearson's correlation, but you can kind of trick Excel. It will be close enough if you use Pearson's correlation on the ranks of the x and y values. We will see how it is done in the next slide. Okay, so what we have is a set of data. We have the mother's age, how old the mother is when she's pregnant, and the infant weight. Okay, we want to see whether are they correlated. So if I take the correlation, okay, of the column A versus column B, it doesn't matter column A versus column B or column B versus column A. It gives me a Pearson's correlation. So how do I do for Spearman correlation? Spearman correlation, basically, I take the values, I rank it based on the mother's age first. So for example, 19, youngest is 19, 20 is the second rank, so and so on. Okay, so there is ties, but in fact I should account for all the ties, but then I just don't bother with it. Okay. After that, I rank the infant weight as well. So I rank the infant weight. Spearman correlation is pretty close if I were to just simply take the Pearson's correlation on the ranks itself. So in other words, Pearson's correlation is the correlation on the data values. Spearman correlation is the correlation on the ranks. Okay, this Spearman correlation is actually very close. There is also actually one difference I should make. Look at here, 21 years old for the mother is rank 3 and rank 4. In fact, I should put both as rank 3.5, 3.5. Then that will give me the actual calculation for Spearman correlation. But this is kind of close enough. Right. Very often, you see actually another measure that Excel will give you, especially when we draw the graph later. Okay. This is what we call as the R-square value. R-square is actually just the square of Pearson's correlation. But R-square is not Pearson's correlation. There's actually a name for it called coefficient of determination. So what does coefficient of determination means? What does it determine? So in this example, if my Pearson's correlation is 0.79977, I square it, I get 0.63963. Okay, basically just square this number. So what does this mean? It's called coefficient of determination because it simply means that here you convert it to a percentage. It means that 63.963% of the variation in the infant weight can be explained by the variation in the mother's weight, a mother's age. Okay. So to make it simply, it means that about 63 or nearly 64% of the infant birth weight is actually determined by the, or can be determined by the mother's age. The other 30% is something else. Okay, so this is what coefficient of determination means. If all the data falls on the straight line, that means all the data is perfectly fitted on the best fit line. It means that all the y values can be determined by the x values. There's no error. Okay, so this is what coefficient of determination means, and inverse and in extension, that's what Pearson's correlation is trying to tell you. Okay, how well the data points fit on the best fit line. In the earlier slide, we actually say that if there is a relationship between the x and y, or the axis, what is the mathematical relationship? We are trying to find the equation. So here, we will construct the equation through a process known as regression. Okay. Now, in the case of the mother's age and infant birth weight, we do have some biological reasons to believe that the mother's age does have influence on the infant's weight. Okay. So this is a paper that I found in 2020 that shows there is a relationship between the mother's age and infant weight. Okay. So what is this relationship? We use, we construct a best fit line for it through regression. Again, because only we have potential reasons to believe that there is such a relation, we can construct a line. Okay. Very simply, we are trying to draw a linear line. A linear line will give you a general equation of y equals mx plus c. Okay. So what it means is, this is through a regression. It's actually a linear regression, and we are doing it through what we know as the least square method. You are really trying to make sure that the errors on both ends are the same. On the top part, above the line and below the line are the same. Okay. So there is a mathematical way to draw a best fit line. And what you're trying to determine is what is the gradient and what is the y-intercept. Okay. Otherwise, in secondary school, what you learn is you kind of just place a ruler to see what is the number of points above, number of points below to be more or less equal, and the size to be more or less the same. Okay? But there is, what I'm telling you now is there is a mathematical way of determining which line is the best fit line. Okay? In Excel, all you need is to have a scatter plot, then you add the trend line. You click on the data points, and then you add a trend line. You can get the best fit line. Okay, so based on this equation, our infant birth weight equals to 17.014 of the mother's age plus 2,227.4. Is this equation reliable or not? The reliability is based on Pearson's correlation. The higher the Pearson's correlation, or the higher the R-square value, the coefficient of determination. Just remember, if Pearson's correlation goes from -1 to +1, correlation of determination, which is R squared, only goes from 0 to 1, because -1 times -1 is 1. So the reliability of this equation is actually based on Pearson's correlation, which then is based on your coefficient of determination. So you look at here, is 64% reliable. It's up to depending on the type of studies that you're dealing with. What I want to explain here is, even if the equation is reliable, it is only reliable up to the data points that we have. Our lowest age for the mother is 19 years old, highest age is 27 years old. So it's only reliable within this range. That is called your interpolation. We can mathematically put any number into the mother's age that's beyond this range, but that is not going to be reliable. That is called extrapolation. Okay? For example, mathematically you can estimate what is the infant weight if the mother is pregnant at 100 years old. It's going to be nearly 4 kilograms. Okay? But at the moment, we still do not have a pregnant mother at 100 years old. Similarly, if you learn in secondary school about Hooke's law, there is a limit of proportionality. Beyond that, the spring breaks. Okay? So you cannot extrapolate. You cannot extrapolate indefinitely as well. Right? So if you do the opposite, if the mother is going to be, you put 0 into the mother's age, that means a newborn girl can have an infant of 2.2 kilograms. That doesn't make sense as well. Okay, so always take care, are you extrapolating your results? Okay, at the same time, we also need to take note of this concept known as spurious correlation. Now, spurious correlation is just simply anything can be correlated. Any events can be correlated. It's actually not easy to find Pearson's correlation to be exactly 0. Okay? But it could be due to unknown factors, or it could be just due to chance. So we'll look at some of the spurious correlation and see what it really means and how ridiculous it can be. Okay, from this website. You can go and look at it by yourself. So I picked 4 of them. Now when you see 2 lines, because the x-axis is by years, you see 2 lines, basically I'm telling you that these 2 points forms one xy pair, from one xy pair and so on. You plot it, the correlation will be pretty high. So if you look at it here, divorce rate in Maine, which is a state in North America, is very well correlated with the per capita consumption of margarine. That means how much margarine on average a person is consuming. Look at the correlation. R is 0.99. Very well correlated, but it doesn't mean anything. Okay? Or people who drown after falling from fishing boat is very well correlated with the marriage rate in Kentucky, which is another state in North America. Okay? It's 0.95. How about the number of letters or the spelling of the winning word in the National Spelling Bee competition is very well correlated with the number of people killed by venomous spiders. Look at the trend. One goes up, the other goes up, one comes out, the other comes out. The correlation is about 81%. Okay? Or US spending on science-based and technology. Look at the trend. It's almost meeting the same line versus suicide by hanging, strangulation, and suffocation. It's actually 0. The Pearson's correlation is 0.997. Okay, although the axes are different. So this is actually a very important example to show you. What we are trying to say is, or what I'm trying to say is, correlation does not equals to causation. Everything can be correlated doesn't mean something causes something. Okay, I repeat, correlation does not equals to causation. This is a very important aspect. Okay, in a lot of false news and so on, they will use this concept that correlation is causation, but it's actually not. Okay, we can correlate anything, literally anything. Okay. So to the last part, last subtopic, how are we going to present our experimental data graphically? Okay. I will show you a number of graphs. We can actually do scatter plot. What I'm trying to encourage you to do is, or let you know is, it's actually very important to graph the data first, okay, between the relationship of the variables, rather than just directly performing correlation and regression kind of blindly. Because why? There's actually this whole aspect of statistics known as exploratory data analysis. You should always look at how your variables relate to each other on a scatter plot first. And scatter plot is a very easy way of doing things. So what I'm going to show you next is an example. What will happen if you just have an X and Y column and you don't do a scatter plot, but rather you just do a correlation, or you just force a straight line graph across it. So we'll see about that. Okay, this is my example. Look at the graph on the left. Now this graph is actually a mathematical relationship. Okay, basically your y equals x squared plus x plus 1. Okay, I construct the points using your quadratic equation, and the correlation is actually very well. It fits on the best fit line. But if I don't do the scatter plot and I just blindly assume that there is a straight line across it, look at the correlation now, it's perfectly 0. In fact, this is about the only time I see a correlation, coefficient of determination equals 0. Okay, so you can force a straight line graph through something that has a perfect mathematical relationship, just that it's not a straight line graph. Okay, so this is what happens when you don't plot your graph and you just kind of perform your regression blindly. Okay, at this point, the formal part of the lecture is completed, but I'll kind of use the next few minutes to explain to you that there are other type of regression, and these are our syllabus. You may not even want to look at it. Okay, so what we have done in the previous slides is your simple linear regression. Okay, or sometimes in your tutorial or in your lab, we'll look at multiple linear regression. But there's actually other forms of regression. Okay, I'll give you 10 of them. One of them is your logistic regression, where the dependent variable is just yes or no. So you can actually use logistic regression when you're looking at study time versus sleeping time versus everything. You get the A or not. Yes means you get A, no, you don't get A, or you pass the exam or not. Okay, that's logistic regression. Poisson regression is when the dependent variable are counts. That means whether do you get certain things based on count data. Linear regression, your dependent variables are not integers. They are real numbers floating. That means you have decimal point. Poisson regression, the dependent variable are actually integer. Quasi-Poisson regression is when you have the dependent variable are integers, but it has a very large range. That means you may go from 0 to 10,000. Okay. When there's a large dispersion of range in your dependent variables, then you use quasi-Poisson regression. Okay. Negative binomial regression is very similar to your Poisson regression, just as based on a different assumption. Okay, so how do you use it is a totally different aspect. Okay, the fifth is ordinal regression. Ordinal regression is used when your dependent variable is a scale data. Okay, think about student feedback. You're from strongly disagree, agree, strongly disagree, disagree, agree to strongly agree. Those are your ordinal data. So if you're trying to predict, trying to estimate ordinal data, you can use ordinal regression. Cox regression is when you have survival, the dependent variable is a time to event. So it's very useful for cases like, you're trying to predict what are the variables that can you're trying to estimate what are the variables that can predict the time between, let's say, first or second infection, first or second anything, accidents or whatever stuff. Okay? Or first time you encounter something, second time you encounter something, what is the time difference that you can use Cox regression. Topic regression is when it's very similar to Cox regression, except that the dependent variable is restricted or censored. Okay. For example, let's say you're trying to find out the time between first infection and second infection, but within your study period, there could be patients who never got the second infection. So you kind of just remove them. You are censoring the data. So those are called censored data. Topic regression will be quite useful on this. Quartile regression is when the dependent variable you are trying to predict is quartile, first, second, third quartile, or percentile. Okay, so it's a bit similar like your ordinal regression, but the scale is a bit more rigid. Elastic net regression is when the independent variables are highly correlated. Yes, so when you're performing regression, there's actually an underlying assumption that the independent variables are not correlated. There is very low correlation between the independent variables. But sometimes that is not the case. Sometimes if we remove all the independent variables that are correlated, we end up with nothing. So we are stuck with independent variables that is correlated to some extent. Then we can use elastic net regression. Okay. Partial least square regression is when the independent variables are correlated, or when there's a lot of independent variables. Okay, we do this quite often in genetic studies because there are tons of genes. Okay, humans have about 23,000 genes, so I can use the expression level of the 23,000 genes to predict something. That means your independent variables, there are 23,000 of them. So we can use partial linear square regression. So this is our syllabus, which means that if you need to learn them, you have to kind of read up or at least know that these are available. Regression is a very big topic in statistics. If you are going to do statistics at a university level, regression is a 1-year subject. There are at least two full modules on it. Okay, that's all that I have for you this topic. See you in the next topic. Bye bye. Have fun.